This is the lesson video for AP Calculus AB on section 3.5 on the derivatives of trig functions. So what we're going to do in this section, I'm going to go through where these derivative rules come from. A lot of this is just going to be practice, and then I want to show you a couple of things on the calculator that you can use, especially down the road when we start doing more problem solving with the calculators. So the first thing I want to show you is where our two main derivative rules come from for trig functions. So really, when we're dealing with trig functions, if we know the derivative of sine and the derivative of cosine, then we can develop all the rest of the derivative rules for the trig functions very easily. So I wanted to show you that the derivative for the sine function can actually be derived using the definition of a derivative, and it's fairly easy to do. So to do this, there are two limits that you have to know. And I'm not going to go through this on the calculator, but you can look at it on your calculator. This one you already know. The limit as h approaches 0 of sine h over h is 1. We saw that in terms of x, but it's the same thing. This limit, the limit as h approaches 0 of cosine h minus 1 over h is equal to 0. You can do that with the calculator. You could multiply by the conjugate. There's a couple of ways that you can evaluate that, and you can use some trig identities to solve that one out. But the main thing is that one is going to be equal to 0. Now, on your calculator, if you were to graph the sine function and then have the calculator graph the derivative of the sine function, which is what's going on there, then you would see that the derivative of the sine function looks like the cosine function. And in fact, the derivative of sine is cosine. So I'm going to show you here why that is the case. And what I've got here is the sine function, and we're using the definition of a derivative to solve this out. So if I want the derivative of the sine function, I'm taking the limit as h approaches 0 of sine of x plus h minus sine of x divided by h. And I'm going to use some trig properties here to rewrite this in a different form. So this limit can be rewritten as the limit as h approaches 0. And there was a composite property that you learned back in pre-cal that you may or may not remember. But I can rewrite that sine of x plus h as the sine of x times the cosine of h plus the cosine of x times the sine of h. Okay, and then I still have that minus sine x there that was there before, and that's all divided by h. Okay, so right now this looks like kind of a mess, but if I group these things together correctly, it becomes pretty apparent how this is going to work itself out. So the limit as h approaches 0, and what I'm going to do is I'm going to take the two terms that have sine in them, sine of x, this term, and I'm going to factor out the sine of x from those two expressions. So that would give me the sine of x times the cosine of h minus 1, and that's all divided by h. So plus we have the cosine of x times the sine of h, and again, all divided by h. Okay, so if I group these together correctly, it'll become really obvious how this is going to work itself out. So I've got the sine of x multiplied to the cosine of h minus 1 divided by h plus the cosine of x times sine of h over h. Okay, so remember, it's the limit of all of that. And when I apply these limits, remember this limit at the beginning, we said this one was equal to 0. So I have 0 times the sine of x. This one we said was 1. So in the end, what I have is 0 plus cosine x times 1, or the cosine of x. Okay, so that is the derivative of the sine function. Now, I don't need you to know how to solve that out. The main reason that I wanted to show you that is because when we do these derivative rules as shortcuts, we're always just shortcutting the definition of a derivative. So if we went back, we could look at the power rule in the same way, the product rule, the quotient rule, and then the derivative rules that we're going to be doing in the future. They can all be proven this way, but we're going to accept for the most part that this has already been done, and we're going to use the rules that are given to us. So in the end, we could actually do the same process to get the derivative of the cosine function to be negative sine. So if you look at these first two derivative rules, those are what I call kind of the base trig derivative rules. derivative of sine is cosine, the derivative of cosine is negative sine. If you know those two rules, the bottom four rules here can all be developed using those two rules. So for example, the derivative of tangent is sine over cosine. So if I know that tangent is sine over cosine, I could use the quotient rule, and then I could show that the derivative of tangent is secant squared, or the derivative of secant x is secant x tangent x, and so on. So in the end, we've got 6 derivative rules that you need to memorize. But the nice thing is, as long as you know these two, you always have the fallback option of figuring out the other rules when necessary. So for example, we don't use these last two functions very often. We don't use cotangent and cosecant very often. So it might be that by the time you really need that in a problem-solving situation, you haven't done it in a while and you can't remember the derivative of cotangent. Well, your fallback option would be, okay, well, I don't know the derivative of cotangent, but I do know that cotangent is cosine over sine. And now I can use the quotient rule and I can figure out what the derivative of cotangent is. So like I said, you should memorize all 6 of these, but as long as you know sine and cosine, you're kind of covered, just in case you forget one of those other 4 rules. Okay, so let's move on here. And what I want you to do next is actually a lot of practice problems. So I'm going to have you pause the video and go through quite a few practice problems. So these next 2 pages are all practice problems. This one's got 6, 7, 8, about 10 problems. And then over here, you've got some simple motion problems dealing with the derivatives of trig functions as well. So I want you to go through these 2 pages of practice problems. I want you to pause the video, work through these quickly, and then when you come back, I'll show you the solutions to them. Okay, and here are the solutions for those problems. And really the idea here is, like I told you before, we're just going to keep using rules that we already know. So it's not just the derivatives of the trig functions here. We're combining that with all of those basic derivative rules we did before, like the product rule, like the quotient rule, like the power rule. Those are all going to show up. So for the first one here, you can just see derivative of 1 over x is negative 1 over x squared. Derivative of sine is cosine. So pretty simple. Second one, we've got x over 1 plus cosine x. I'm just using the quotient property there. Not really anything tricky about it. For the third one, x minus 3 sine x. Again, I'm just taking the derivative of the sum of terms. So take the derivative of each term independently. For this g of t function, we're just doing the product rule. Not really anything tricky about it. For the sine x over x squared, what I do want to point out on this one is that there is an x that you can cancel out from both the numerator and the denominator. So when you cancel out those x's, just keep in mind, look at the original function. The original function was undefined at 0. So we had a 0 divided by 0 value. So that tells me I've got some sort of discontinuity in my function, which tells me that the derivative is not going to exist at 0. So when I cancel out that x to make the denominator go from x cubed or x to the 4th to x cubed, I'm not eliminating anything important about the derivative because the derivative is already not defined at 0 because the function's not continuous. The next one here, the only thing that I have said before on these is when you can factor your derivatives, it's nice to have them in a factored form, and you'll see that a little bit more in a few weeks when we start getting into applications of derivatives and analyzing functions. We'll start to need to be able to know where the derivative is 0 or undefined, and if it's in a factored form, it makes it a lot easier for us. For the one at secant theta over 1 plus secant theta, I didn't show all of the simplifying steps here, but the main idea is most of the time when you take your derivatives, the first step that you do is kind of the easy part, following the rule, and then the algebra that you have to do afterwards, that's typically where you're going to be a little bit more challenged to get your solutions into a form that match up with, the answer that you're given on a multiple choice or the answer that's in the book or, whatever the simplified form is that, you're looking for. Here we've got x over sine x. There's really nothing tricky about this one. Very straightforward. It's just quotient rule. Now down here at the bottom, I wanted to show you this one and make sure that you think about this. So on this problem, the intent here is not for you to take 13 derivatives. So you can see it says take the 13th derivative of the sine function. The intent here is for you to figure out the pattern. So the derivative of sine and the derivative of cosine both have the cyclical behavior when you're taking the derivatives, meaning that if I take the derivative enough times, I'm going to end up back where I started. So for example, the derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, and then I get back to sine again. So I've essentially completed one cycle, and you can see that took 4 derivatives. So now using that pattern, I can figure out, okay, if I need to take the 13th derivative, how many of these cycles did I complete? And then how many extra derivatives do I have after that? So you can imagine that after 12 derivatives, I've completed 3 cycles, and now I've got one more derivative to go. So the 12th derivative would get me back to sine, and then the next derivative after that would be cosine. Okay, so like I said, both sine and cosine have that cyclical derivative behavior. Now the next problem is just to show you that that doesn't work with the other trig functions. So here we've got cosecant x, and if you take the derivative, we get negative cosecant cotangent. You take the second derivative, it's obvious right away we're not going to have a cycle of derivatives here this time. So you get a messier derivative, which clearly is not going to get me back to cosecant x if I keep taking derivatives. So sine and cosine have the cyclical behavior, the other 4 do not. Okay, and on this next page, it was just some motion problems. These are pretty straightforward. We've already seen position, velocity, and acceleration. This is just showing you the same information now using trig functions. So we've got the position of 5 cosine, the velocity of negative 5 sine, and the acceleration of negative 5 cosine t. And you can see here's the graph of all of those functions. And the idea is there's a relationship between the position and the velocity and the acceleration. So we saw that previously when we looked at the graph of the function and its derivative. You can see those same relationships here. So for example, when my position function hits a horizontal tangent, so like right here, I've got a horizontal tangent. Look at the value of the velocity graph at that point. The value of the velocity graph is 0 there. So as I would expect, because the velocity is the slope of the position function. And you can do the same thing with the velocity and the acceleration. All of those same relationships apply. Okay, then when is the weight moving the fastest or the slowest? But remember, the fastest weight is going to be when our velocity is the furthest from 0. And you can see that's going to happen, you know, at these points on this velocity graph. And using the fact that the velocity graph is working off of a sine function, then it's pretty easy to see why we're at pi over 2. And we're just going to go with multiples of pi over 2 based on the fact that it's a sine function. And then it's going to be the slowest, the velocity is the slowest when the velocity is 0, or the speed's the slowest when the velocity is 0. And you can see here, you know, we've got these points where we're at 0 on the velocity graph, and that's where we're getting those multiples of pi, 2 pi, and so on. Okay, so fairly simple. The last thing I wanted to show you here is just a little bit of practice with your calculator. So this is not anything that I want you to do by hand. I really just want to show you how this works on the calculator. So let's say you wanted to take this function, the tangent of x over 3x, and you want to find the tangent line and the normal line. We could do this by hand, and we could get exact solutions in terms of the trig functions. However, what I want you to do here is actually practice storing values in your calculator. And this is something that's going to be really useful to us when we get to problem solving. In a few weeks, we'll start doing a lot of problem solving with derivatives. And then in the second semester, we'll do a lot of problem solving with integrals. And a lot of times we'll need to solve some algebraic problem along the way. And we'll need that number, and we'll have to use it again later on. Whatever the result is, we have to use it again later. And the result may not be like a nice integer or a nice rational number. It may be an irrational number where we've got a decimal answer, and you know, we've got to start thinking about rounding issues. So that's really what we're looking at here. So we want to find the equation of the tangent line and the normal line. Now notice the setup that we have here. This is just kind of our standard point slope formula. Y minus k is the slope times x minus 4. We've seen that before. And the only thing that's changed here is now we multiplied the m through and then move the k over to the right-hand side. So what we're trying to do is rewrite this in a form where we could actually graph it on the calculator. So the k value would be whatever the function value is at x is equal to 4. And then the m value is obviously going to be the slope. So I'm just going to show you, I'm not going to go through all of the steps that are outlined here. I'm just going to show you how to store these on the calculator. And then if you want to go back and work these out and get the actual equations, you can graph them that way. But I'll show you on the calculator how this works. So on your calculator, what you can do, first of all, notice that I entered as y1. I said y1 is tangent x over 3x. So you could look at the graph if you want, but for what I'm going to do right now, I'm not that interested in the graph. Make sure your calculator is set to radian mode. But the first thing I want to do here is I want to find that k value. I want to know when the function value, or what the function value is when x is 4. So as a shortcut, I can hit alpha trace, and that is referencing now the y1 function. So that was my tangent x over 3x. I'm going to plug 4 into that. So that's what the function value is approximately when x is equal to 4. Now, if I start going through and rounding, then I'm going to lose some accuracy in this answer. So this calculator is actually calculating this beyond what it's displaying. I think it goes out to maybe 20 decimal places. So if I want to keep as much accuracy as possible until the very end, what I can do is store this value. We're calling this the k value. So I'm going to hit the store button, which is right above on. So I hit the store button, and I want to store that as k. So notice that k is above the open parenthesis sign. So I'm going to hit alpha and open parenthesis. So I want to store that y value as k. And then we can do the same thing for the derivative. We need the derivative of the function at x is 4. So I'm going to do math 8 to get the derivative. And I'm taking the derivative of my y1 function. So I don't need to retype the name of the function every time. So I entered it as y1 because I didn't want to have to keep retyping it. So I'm going to hit alpha trace to pull up this shortcut to these y's. And my function is y1. And I want to evaluate that derivative when x is equal to 4. Okay, so there's the value of my derivative. That's the slope. And now we can go through and actually find the equation of the line using, and I'll go back over here to my notes and show you, using this equation right here, I can now get the equation of the line, and I haven't rounded anything until I get to my very last step of writing out the equation of the line, because I know what the slope is, accurate out to probably 20 decimal places, and then I can do negative 4m plus k on the calculator, and I can get that corresponding y-intercept for the equation of that line. Okay, so the calculator stuff's not that big of a deal right now, but I'd like to show you these in little bits so that when we really get heavy into using the calculator, I'm not having to teach you everything from square one. So practice with that a little bit, but we're not really going to use calculators a lot for now. In another 3-4 weeks, we'll start to get into them more and more and more. Okay, that's all I have for you for this lesson. Just make sure you practice a lot with those trig derivative rules, and make sure you've got all 6 of those memorized.